Soon, can you check?
Yeah, it's on.
Great.
Yeah, it's on. Can you change your name? Your name looks like a... Can you change your name? Your name looks like a...
I hear some weird echo. Does everybody hear that?
Is that better, or do you still hear an echo? Okay, Sung, let's get started then, I guess.
Hello everyone, welcome to 2020 International Conference on Mining Software Repositories. My name is Sung Kim and General Chair here.
Hi everybody, I'm Sarah Nadi from the University of Alberta, and I'm the program committee co-chair.
Hi everybody, I'm Georgios Gousios from the Delft University of Technology, and I'm also the program co-chair. So what is typical when a conference starts is that we, as program chairs, we give a short overview of what the conference procedure was like, so how the review process was handled and so on. But this year our setting is not typical. It's the first time that this conference is running completely online. So what we decided to do instead is that we try to pre-record our talk and have everything on YouTube shared with you before the conference starts. Since we have you all around though, we would like to talk a bit about how the whole virtual setup went on and what interesting experiences we had building it.
So this is how things went. So typically the conference, for those of you who don't know, MSR is co-located with ICSI. The date was actually end of May. And so by March, we had finished selecting the papers, and then the pandemic hit, and ICSI decided to postpone to October, and MSR said, okay, we'll postpone as well. So at that point, we selected the papers. All was left was the normal group together in 2 sessions. And so Georgios and I said, oh, okay, we still have a lot of time till October, and we just set things aside. Suddenly, beginning of May, ICSI decided to move virtual and into July, and then it didn't make any sense anymore for us to wait till October. So instead of having 6 months to prepare a typical program where we were just going to group papers together, we now had to figure out this whole new setup, and we only had less than 2 months to do it. So this was quite an interesting experience.
We thought about various alternatives, such as live presentation versus pre-recordings, YouTube versus Zoom, and how to handle the questions that we might have from the audience and so on. In the end, we decided that what's more important and what's the reason that people go to conferences is basically in-person interaction. So we tried to keep this in spirit for this virtual MSR. This is why we opted for all paper presentations to be pre-recorded, and that the online sessions would be dedicated only to Q&A and discussions. The conference has been running since the morning. My personal feeling, I think, is going pretty well on that. You can find all the details about the program, and we also created a short video on how to explain and navigate the program. The program is on the website, and there are links there to the various live YouTube sessions that we're having. One of the live sessions is that one, the one that we're in. We also have quite a few Ask Me Anything sessions. It's 3 in total, and those will be live streamed as well. So we invite everybody to join those. The recordings will stay on YouTube so that anybody can watch them after we are done with this conference.
Yeah, so organizing MSR 2020 was definitely interesting and stressful. I definitely had my freaking out moments at different times. And it also presented new experiences that we never thought we were going to do. So for example, to prepare our conference opening, this is what we had to go through.
So,
Oops.
So thanks a lot for coming. So today we are going to talk about 2020 International Conference on Mining Software Repositories. I'm Kim, and I'm general chair on this conference.
My name is George.
I'm sorry. I waited for you.
Okay. All right.
Okay.
Okay, it's a lot of fun.
So Sung starts, and then Sarah, and then me. Okay.
So who would have thought we'd have our own MSR bloopers for this, but definitely an interesting experience. I'm glad we got to this day, and very excited to say that we have 324 participants so far, not including our YouTube audience. So this is by far the largest MSR ever. So we're super excited to have you here.
We have an interesting keynote coming up, but we know that you are here mostly for the keynote, but we would like to steal some of your time to present to you the award winners for this year's MSR. So we, as you know, for MSR, we have multiple types of awards. The first award, the Foundational Contribution Award, goes to Jonathan Maletic and Michael Kohler for the source ML infrastructure, which addresses many hard problems in source code parsing and has fostered a wide range of research innovations throughout software engineering. The Rick Holt Early Career Achievement Award goes to Alberto Bacchelli for his seminal contributions to modern code review. The Most Influential Paper Award goes to Marco D'Ambros, Michele Lanza, and Romain Robes for an extensive comparison of bug prediction approaches. This is a paper that appeared at MSR 2010, and we had a committee of various experts that went through the papers from that year and selected this as the one that had most of the impact throughout those 10 years that passed.
Congratulations.
The honorable mentions for that paper goes to Gregorio Robles for the paper Replicating MSR, a study of the potential replicability of papers published in the mining software repositories. So we are giving also distinguished paper awards for this year. The first one goes to Yalin Liu, Jinfeng Lin, and Zheng Lilat Huang for traceability support for multilingual software projects. Congratulations. The second distinguished paper award this year goes to Nicholas Gold and Jens Krinke for ethical mining, a case study of MSR mining challenges. Congratulations again. The third distinguished award, paper award this year goes to Yang Chen, Andrew Santosa, Ming Yang, Abhishek Sharma, Asankaya Sharma, and David Lowe for their paper, A Machine Learning Approach for Vulnerability Creation. Congratulations. We are also giving out FOSS awards, we call them. It's for contributions to open source through research. This year, we're giving the award to James Walden for his paper, The Impact of a Major Security Event on the open source on an open source project, the case of OpenSSL. And we're also giving awards for the data showcase track. And this year, the award goes to Esteban Para, Ashley Ellis, and Sonia Haiduk for their dataset GitterCom, a dataset of open source developer communications in Gitter. Finally, the last awards that we're giving out is to recognize the effort that all our reviewers have put in their reviews. From those, we selected the ones that put just a little more effort to make the review process more, to make their reviews much better. And we have selected, we have gone through all the reviews, we observed the discussions and so on. And the list of distinguished award reviewers this year includes the following people: Serge de Meyer, Andre Horer, Nicolos Santalis, Mauricio Anis, Malek Naz, NIAB, Jesus Gonzalez Barahona, Francisco Servant, and Philip Leitner. Congratulations, everybody, and thank you for the excellent reviews.
Wow. So I'm so excited already about all the words. Congratulations again. We wish you a great experience at Virtual MSR 2020. Then now this takes us the highlights of the day. So it's really our great honor to have Satish for our keynote speech. He got his PhD from the University of Wisconsin Medicine, and he was a member of the technical staff at Bell Lab, where his research focused on the program analysis, domain-specific languages, and data communication protocols. And after that, he was a research staff member at IBM Research, where he research focused on the bug findings and verification software synthesis and test automations. And his work on bug finding actually shipped in the IBM Java static analysis product, which is really great. And his work on test automation was also dated in the IBM's test service offering. And after that, he worked at the Samsung Research America, and where he led the advanced programming tool research team. And his work on the memory profiling on the web apps was included in the Samsung's Tizen IDE, which is very popular in Samsung. Now he is with Facebook, and then he is also a ACM distinguished scientist. Today, he will give us a very interesting talk about machine learning for developer productivity at Facebook. Let's please welcome him together.
I am now unmuted. Thank you, Sung. Thank you for inviting. Should I put my slides in presentation mode?
Please.
Yes, please.
Okay. All right. Do you see the projected page?
Wonderful.
Okay, wonderful. Well, thank you, Sung, and all the organizers of MSR for inviting me to give this talk. The mining software repositories community has really been at the forefront of this business of using data-driven methods in software engineering. From what I gather, this is the 17th year of this conference. So what an incredible journey and what an incredible impact. It's really an honor to speak to all of you and share a little bit of what we have done at Facebook in terms of bringing machine learning based techniques to developers and developer workflows. Okay, so now just to give you an idea of the scale of operation at our company, and these are not actual figures, these are kind of for illustration only and to convey sort of the order of magnitude ratios between these items. So you can read it as the number of code commits per week is an order of magnitude more than the number of developers, and number of tests is an order of magnitudes more than the number of code commits weekly, and so on and so forth. So you can see that the scale of operations is large, and also the engineering at Facebook moves fast. So scale is always a challenge in any company, but it can also be seen as an opportunity. So we operate at scale. We have big code repositories. Nowadays, of course, the term big code itself has become a standard term. We have code change histories, the metadata associated with those histories. We have histories of builds, tests, their outcomes, and so forth, and many other things. So all of this information is collected and has been collected over a number of years. And so the question is, can we leverage some of these resources to in fact fight the scale with and use the scale itself as an opportunity rather than a limitation? So in this talk, I'd like to talk about two different topics. One is about continuous release and continuous integration and how simple ideas from machine learning can be helpful there. And then in the second part of the talk, I will talk about some of the work in predicting bug fixes that we have done at Facebook. And then I'll wrap up with thoughts over some of the other ideas in this space. So let's get into continuous release. And when I started at Facebook, I found that the software release process is very much different from what I had seen earlier in my career at other companies. Long time ago, we were used to thinking about, well, you cut software releases every so often, maybe few times a year, and that's it. But nowadays, we see that software release process has completely changed. So why did this change happen? Well, over the years, the industry has come up with a bunch of different ways to release software in small, sort of safe chunks and get it validated out. And many ideas in software engineering, such as test-driven development, agile development, and also continuous integration and continuous release, these are really enablers to let out small pieces of code in small chunks that are easy to manage and easy to get out, easy to backtrack from, and so on and so forth. So that movement has already been there. At Facebook, we now have a continuous release process, which I'd like to just introduce very quickly here. So we have code changes coming through our quality pipeline. So there are a bunch of quality checks that are run, including testing. And these are all folded into, you can think of as a master branch. And then from the master branch, every so often, a release sort of pushes out to employee. And here I'm really talking about facebook.com. I'll get to the mobile in just a minute. A release gets rolled out to employees or dog fooders. And if there are any push blocking alerts from those, then you stop things and you address things. But if everything goes well, you release the version, so to speak, to a larger population, maybe 2% of all the users. And then again, you watch for signals as to what's going on. You monitor whether there are crashes and so on and so forth. And again, if everything goes on fine, then you release it to even broader population. And so this business of making new code available to users happens not once every 2 months or 3 months. It just happens pretty much continuously with very small time granularity. In such a situation, it actually forces us to rethink the tools and automations that are required to manage this kind of a process. I mentioned mobile before. So in mobile, because continuous release as you could do on the website, but here we sort of work in granularities of a week. So you have 1 week of development, and then while the next week of development is happening, there is a stabilization part where you do the dog fooding. The app will go out to employees and beta testers, and then you fix those things and get it ready for production. So the principle is kind of similar. So as I mentioned, with this continuous release style of development, we have to work even harder on our tools and processes. So what are those quality processes? So let's take a look at, and here all these colorful small blobs that I'm showing, we will get into what these mean in the very next slide. But you can imagine that as a developer produces a unit of code, which is called diff in Facebook jargon, you run all these quality controls. So you create a diff and perhaps you run these quality checks, and then you update a diff and perhaps you run these quality checks, and so on and so forth. So these quality checks are run over and over again as a developer's code sort of changes and joins the master repository. This does require a lot of infrastructure, which we will get to in just a second. So, but now let me first tell you about what those colorful dots were. So you could imagine that there are sort of layers of quality control. For example, first thing you have to do is to just simply build your product, and you build it for the app and also for the simulators. And then as in many other companies, you run all the linters and static analysis tools that you use. So at Facebook, for example, we use Infer a lot, but you could imagine any of the static analysis tools that are popular running in this layer. And then finally, you have tests. So you have unit tests that a developer often runs, but then you have more system level tests that run sometimes with simulator supports and so on and so forth. So there are several layers of quality control that are applied before a developer's diff can join the master repository. So let's examine that in a little bit more detail here. As I mentioned, there is a master repository, and this is an important point, that we keep the master current. We don't do a lot of development on branches. So a developer comes along, they kind of create a temporary branch and in this diff that they are writing, and that diff gets revised a few times, and finally it joins back into the master repository. And then every once in a while, the head of the repository, which is being shown here in the middle sequence of boxes, that is moved to a release ready branch, which is shown here as in the lower part as a red series of boxes. So here, as a developer goes through between the diffs, they would run all these tests. These are all run automatically. So here, when I say tests, these are really builds and static analysis phases. And then when they are about to land, they want to do a little bit more work. So they would run all the simulation-based tests that take more time. But only when these tests pass, the code gets to join the master repository, as it should. From the master repository, every once in a while, when code is ready to be moved to release ready repository, there are additional tests. For example, you want to make sure that the code does run on physical devices just fine. You look at battery usage and so on and so forth. So that is also you can think of as a further phase of testing. And then when it goes out to alpha users, there is you can think of it as another implicit phase of testing, where if a user experiences a problem, they can simply shake their phone real hard and a screen comes up and they can report the problem they are having. So this is what the alpha testers and the dog fooders, so to speak, would do. And then after that, there would be a phased rollout as I mentioned before. Even beyond that, you have to monitor what happens post-release. So that's where automatic crash reporting and processing comes into play. So crashes are captured automatically. we try to use techniques to automatically find out what is the most likely diff that could be responsible for a crash. And we also look at lightweight techniques to find which is the developer who should be looking at this crash, and so on and so forth. So there are lots of opportunities for data-driven techniques here, and the MSR community, of course, has been on top of this line of work for sure for last several years. But this is not exactly what we'll talk about in today's talk. We will talk about machine learning for continuous integration. So I'd like to take you back to this picture where I showed you places where quality control kicks in, and this ends up being computationally expensive. So how computationally expensive? So you can see some order of magnitude numbers. Again, here there are so many diffs, 10 raised to 5 diffs per week, order of magnitude fewer number of lands per week. In terms of infrastructure, there are tens of thousands of servers, lots of phones, and these hardware resources, we keep growing to supply the bandwidth for doing the testing, but the testing capacity can hit a bottleneck. And when developers encounter a large latency in getting the signal back from all this testing infrastructure, they are not being the most productive they can be. Moreover, by the time your diff is ready to land, other people might have committed their code also, and so now your diff in some sense may already be a little bit stale. And then you could also have other infrastructure issues in the meantime. So when all said and done, this is kind of a screenshot of what something might look like. So you create a code change or a diff and you submit it, and after 45 minutes you see failures of various kinds, and you are bound to be a little bit unhappy. Okay, so that's one thing, but it's also important to understand why this is happening. Why is the work involved per diff or land so large and growing? So let's look for reasons behind that. So the reason to a large extent is that we use monolithic repositories. And what this means is that, as I mentioned before, all the code is essentially just in the master branch, so to speak. There are no other long-lived branches. Every time developers make changes, they have to fold their changes back into the master branch, and everyone stays current with the master. So there are some pros and cons. We will go over that in just a second. But what happens in monorepos and with code changes, that you can now think of the organization of monorepo logically as code dependencies. So you have core libraries, and then you have intermediate targets that depend upon those core libraries, and then you have eventual products that depend transitively on everything. And so if you imagine a code change roughly where it shows on the slide somewhere in the middle, everything downstream in terms of build dependencies is in principle affected, and you have to run all the tests and quality control associated with all the affected things. Intuitively, we know that a majority of tests are not necessarily affected, but because of this transitivity and because of granularity of the make files, you cannot really tell that, and you have to kind of suffer through this curse of transitivity, so to speak. So let's get back to just finish up with why monolithic repos. This discussion has been very well documented by a paper from Google now 4 years ago in CSCM magazine. Briefly, it helps with easy mass refactoring. So someone wants to refactor something, they can go and change everyone else's code, and that kind of becomes part of the culture. There is no so-called diamond dependency problem. merge steps in sort of long-lived branches, there is often this problem of very difficult sort of boil the ocean kind of merges, which is no longer the case with the monorepo, and so on and so forth. But there are costs also. For example, there is constant churn. So your code can be changed by someone who decided to refactor the name of a library. And then continuous integration can be computationally expensive. So let's pick up on this last point here. Continuous integration can be computationally expensive. So here again, we are back to dependencies. We have a code change shown by the colored dot at the top of the screen, and everything downstream in terms of dependencies are those things reachable in the graph sense from there. So all these dots now shown in yellow are build dependencies. And you can see that in a large system, there will be many build dependencies. And there are many build dependencies just because the granularity of make files is kind of high. Make files just simply say that, okay, if I am being told that I depend on that thing, I'm going to assume that a change upstream does impact me. So I have to redo everything. Now compare this to a traditional repository model that you might have seen, for example, in a lot of open source software, where there where there is a notion of versioning. So someone might evolve their library code from a previous version to a next version, but as long as you downstream if you downstream agree to depend on a certain version number of the library, you don't need to update your code immediately. You can continue to rely on a previous version. So this versioning thing kind of breaks transitivity, and it adds tiers to the TIER, tiers to the change propagation, right? Whereas in the monorepo, there is no such natural boundary. But now, while everything that is affected in the sense of a make file dependency, true, it is dependent, but in terms of actual affectedness, perhaps only a subset of those are really impacted, and those are shown here by dark blue circles. So if you had a great way of figuring out change impact propagation, you could weed out a lot of dependencies that make files say that are impacted. Furthermore, we also know that failures might actually show up in only a subset of these affected targets. So ideally, we would like to only run tests where failures might occur, but that's currently very hard to do. So here is the insight that we brought to the work. And there is a paper that I have mentioned here on this slide that describes all of this in much more detail. And the insight is that while we cannot really learn the idea of affectedness, we can learn to predict which nodes in this dependency tree might show failures. So how would that work? So imagine that there are diffs and there are tests. So what you want to do is, given a new diff, and take an existing test and ask the question, is this test likely to fail on this diff? That's the prediction problem. And so as in machine learning, we have to do training and then we have to do prediction. And in terms of building a model, you first featureize both the diffs and the tests, because we are not going to be talking about the exact same diff coming up for testing all over again. And so some of the features that are interesting from a diff point of view are kinds of files modified, the size of change, the kinds of code review comments they have, the identity and the nature of the project, and so on. And then likewise for tests, what's the size of the test, historical rate of failures for that test, and so on and so forth. Some other interesting features actually are joint between diffs and tests. So one of the interesting ones is that in the code hierarchy, how far apart in terms of purely directory structure are the change and the test? Were the code change and the test added at roughly the same time or not, etc., etc. So you create sort of a sampling of these diffs, and you take most tests, and then you run, so to speak, these training jobs at off-peak hours. And then the idea of this is that for each of these pairs of diffs and tests, you record whether it passes or fails, and you store that information in a repository. And next time a new diff comes along, you use the model that you created from the pre-existing data to predict whether the test is likely to fail or not. And then you only run the most likely to fail test. So that's the idea. In terms of the pictures that we saw before, now, irrespective of what the build dependencies say, we run this, we query this model for each of these nodes, and we ask, is this node likely to fail? And you mark the ones that are likely to fail, and you only run those. So that's the idea. And now you can see that you have to run tests associated with a much smaller number of nodes. And there are a lot of details. Many of those are written down in the paper. You have to calibrate the model carefully. We set the classification threshold so that it predicts 95% of the test data correctly. And when we did that, we did find that the number of executed tests reduced by a lot. The capacity usage dropped down quite a bit, so that was nice. The wait time that the developer has to encounter became more build time bounded. So it was no longer the case that we were waiting on an average for a large number of tests to go through. It was more of just the build. So all of these are very nice outcomes for us. Before I finish up this topic, I want to quickly mention this business of test flakiness that many of you might have heard of. And that's the idea that sometimes even tests that are not truly affected can fail for various random reasons. So here, the truly impacted tests were shown in those dark blue dots, but in terms of failures, you could see failures in other places as well. And so what happens with the problem with that is that if you think of all these tests and you have a subset of affected tests that we were showing in dark blue, and you have a set of failures, these failures that are not overlapping with affected tests are essentially flaky failures. And so what if you learn to predict whether a test is likely to fail or not, you might be predicting flakiness quite a bit, as opposed to just the truly failing, the real failing test. The arrow there that says real failures should really be pointing to the overlap of the fails and affecteds. It incorrectly points to the affected box, but it really should be pointing at the intersection. And then if you manage to somehow reduce the amount of flaky failures, then your model is much more likely to be approximating the real failures that you wanted to predict to begin with. So we do a number of things. Most importantly, you run tests multiple times, sometimes to understand whether they are flaky or not, and that's one way to reduce flakiness, but there are other ways as well. So to recap, we use an idea of prediction and in some sense knowledge of previous diffs and previous test runs to train a model to predict this idea of whether a diff is likely to fail on a test or not, or rather whether a test needs to be run given a particular diff. I called out on this problem of flakiness, which ended up being very important. I should also add that there are other opportunities to improve the idea of effectiveness as well. So there has been lots and lots of work on change impact analysis, and perhaps some of this work needs to become sort of more suited to the kinds of deployments that we have to do, and that would also sharpen this idea of reducing the number of tests that you need to look at. So with that, I cannot take live questions. In a live talk, I would have stopped here and taken questions, but let me push on and we will do the Q&A at the end. I'm going to switch gears a little bit and talk about machine learning in code assistance. And I'm going to start with showing the same slide that I showed at sort of the beginning of this talk, that scale presents an opportunities. We have lots of sources of data such as big code and code change histories. So let me now pick up on the idea of code change histories and see what we can do with that. So here is the opportunity part of it. So imagine the evolution of this repository, and between every dot you see sort of additions and deletions, if you will, and this is the evolution of your code. So some of these changes will obviously be adding entirely new files, or maybe just a few lines, or deleting just a few lines, and so on and so forth. What can you do with this information? It turns out that actually quite a bit. You can use this information to automating certain kinds of routine work, and that's exactly what we have tried to do with a different project called GetAfix. At the bottom of the slide, I have written down a reference for it. But let me tell you what GetAfix is and how it works. Okay, so there are several categories of routine work that a developer has to do. So here is one. So a developer might simply recognize that there is in fact a simpler way or a better way of writing some piece of code. So going from left to right, that is one example. A developer might have to refactor their code in response to changes that are forced from time to time. So for example, if people were previously using old API call, they are now encouraged to use new API call. That's another kind of routine change that developers often end up having to make. And then finally, there are small bug fixes. So for example, if there is a bug associated with this line, a developer might want to fix it in this manner. So the exact nature of the change here is not important. What is important is that these kinds of small changes are routine, and the goal of GetAfix project is to try to predict these kinds of changes so that developers don't have to do those themselves. In particular, let's focus on fixing static analysis warnings. And as I mentioned before, at Facebook, we use infer static analyzer quite a bit, and we are going to focus on the warnings that infer produces. Now, we know that at every commit level, so for example, showing one of these dots, there may be certain number of infer warnings at that commit level, and as you move to the next commit level, maybe one of those warnings went away. And if those were infer warnings, then the code change there is quite likely to be the change that the developer made to address that particular warning. So for example, it could be the case that when you went to the next commit level, you actually addressed a warning associated with the line return v.getWidth, and then you ended up adding a small null check in that particular case to make infer satisfied that we are not going to see a null pointer error here. And null pointer kind of errors are still important for Android Java code. So this kind of change is does take place from quite often. Now, if you look at lots and lots of these changes, the cool thing is that you start to see patterns. So the change that I showed in the previous slide is one kind of change associated with fixing a potential null pointer bug. But if you look at lots and lots of changes, there are many different patterns that emerge. So on this slide itself, I am showing you 6 different patterns of remediating null pointer kind of errors that emerge from learning patterns from our existing code bases. And what's really cool is that what I am showing you is in fact GetAfix automatically making these code changes on existing code in response to infer warnings. So all of these are the code changes shown in green are changes that GetAfix automatically recommended that that would fix the infer warnings. So this is kind of a real case of program repair, if you will. In a limited sense, we are not fixing all kinds of logic bugs. We are fixing here a specific kind of bug. Okay, so in terms of what the user sees previously, in our internal code repository management systems, you would see something like this, that infer, which is sort of packaged as a linter, raise this kind of a null dereference warning on line 69 and a small explanation. And now what happens is that in addition to the same explanation, we also show a small code change, which is take away that line and add that line shown in green, and then we present a reject and accept button. A developer can choose to accept the recommended and the code change recommended by GetAfix and move on. So this kind of addresses the developer workflow in a very powerful way, that as they are looking at sort of automated code review, if you will, they can along with also fix their code, and that's that. So they don't have to kind of change context and go to their IDE and make that fix and so on and so forth. This system has been quite, the experience has been quite good. Here we have shown what happened to these GetAfix NPE autofix recommendations. One important happy news here is that over 40% of them were just accepted by developers. That's very nice. It's very nice, but it's not everything. But it's still very impressive, because we know that developers are very persnickety. So in 9% of the cases, we showed a fix, but our developers did not accept the fix recommended by GetAfix. Instead, they wrote a semantically equivalent fix themselves. So that shows that they are extremely particular about the way in which they fix a particular issue. And given that they are persnickety, given that having more than 40% of the suggestions of the autofix suggestions accepted is actually pretty good. So let me now quickly go over how does GetAfix work. So this happens in sort of 3 steps. You first localize AST level edits from human fixes from the past. You mine patterns from those edits, and then you apply these mined patterns to new bugs and rank the fixes. So let's go through each of them. First, you have to localize AST edits from human fixes. So what does that mean? Well, we have a sequence of code changes, as I mentioned before, and in each of those changes, there is a before version of a file and there is an after version of the file. And you could have, of course, multiple files associated with each of those commits. So you take one of them and then you will take each pair in turn, but you take one of them and then what you do is you do a tree level comparison. So there is an algorithm that we use that maps equal nodes to one another, and that helps see what is changed as you went from the before to the after. So, and there is a kind of a standard algorithm to do this. It's packaged in a tool called Tree. We use a similar kind of tree differencing algorithm here. So you could imagine if you retained all the nodes that map to one another unchanged, you might see that maybe the label of some node got updated. That's been shown here on this slide in yellow. Or you may discover that, well, some nodes were, I pressed next too soon. Some nodes were removed or some nodes were added as shown in green. So now let's look at the before and after having annotated with what was updated or added or removed. And there is a move primitive as well, but that's not being shown here. And then you capture small code edits. So small code edits being captured are shown here in sort of this brief animation that we considered a AST level code change just with the yellow nodes or with the parent of it. And then likewise with this red node where you found something, the parent has to be sort of the same. That's the idea, that you find these before and after pairs, and likewise you capture these nodes. So the idea is that you want to break down a change at the file level into small changes at the AST level, and while capturing these small changes helps discover generalizable patterns. So that's the reason why we do that. But in any case, we collect all these small AST level changes, and then we go to the next phase. So these are, let's say these are all small AST level changes. We are going to mine patterns from these changes. So what does that mean? Well, if you have two changes that kind of look similar to each other, we are going to create an abstract change out of those. So here is what happens. So let's say A and B were two changes, which means there was a before and there was an after. And as you can see on this slide, A and B are actually quite similar. The differences are that the variable, the receiver variable, so to speak, is different between A and B, and also the method called is different between A and B, but they are very similar. So what we would like to do is to capture this pattern as an abstract pattern, and then use it where needed. So here that abstract pattern is being shown as AB, and you can see that we have eliminated the specific local variable names v and list and specific method names, and we have instead used sort of meta variables to capture the pattern. And then you keep doing this as long as useful patterns arise. So as you go up this tree, you are going to have more and more abstract patterns. And in the end, you are going to just, if you force everything to merge together, you are going to just say, okay, there was something, it became something else. So that in of itself is not particularly useful. What is useful is that if you look at this as a forest of interesting code edits where the roots of each of the trees in the forest capture something that is reusable. So that's the idea of pattern mining. Now, I need to tell you about one more bit of detail, that how exactly did we write those two A and B patterns into this common patterns. So it turns out that there is a very elegant way of doing this based on the idea of anti-unification, and other researchers have presented those ideas as well. I have put a reference here. And the idea is that you are going to create a single tree that represent multiple trees, and in a way that you introduce holes where these trees differ, and you maintain a substitution table that will give you original trees if you substitute the value of these, if you substitute the concrete items that we abstracted out in place of holes. So let me illustrate that with a quick example, because it's much easier to see in an example. So let's say these were our two edits, left before, right after. And so this is kind of shown in tree form, the left tree that was before and the right tree that's after. And now I'm going to take the befores of two different edits. So we had an edit involving A and B and another one involving C and D. Let's try to do the anti-unification. So we mark out nodes that are actually the same, no problem. And then we run into a node that is different. So here we introduce a hole, and we'll name the hole H0, and we'll keep track of the information that H0 in the first tree was A and the second tree was C. And we do the same thing for B and D. Now, and introduce the name H1. Now let's come to the afters, knowing what the mapping was from the before case. And we find many nodes that are same, and then we come to A and C. At this point, we notice that in fact H0 was exactly the common variable that we had introduced there. So we can in fact write H0 in its place. We keep moving, and again we find an A and C, so this has got to be H0 again. And then we find B and D, so this has got to be H1 again, and we are done. So it turns out that you can in fact write this pattern in this form, where we have completely abstracted out from the specific local variable or method names that appeared in the concrete edits, and we have abstracted them out into this abstract edit pattern while keeping the nature of the edit. So this is again one way of showing that. And we are going to recover many such code changes, all from just the remediations of null pointer warnings in infer. So these are three that I'm showing here, but there are many others. So now let's move to the last part of this, that how are we going to apply these mind patterns to new bugs and fix them. So let's say a static analyzer told us that on line B, there is a bug here, right? So that's shown in the red box there, and that bug is a potential null pointer bug. And you have certain patterns here, 3 patterns that let's say seem to apply to this case. So, well, you could kind of apply all of them and see what happens. So I have taken the pattern. Let me show the P1, P2, and P3 one more time. So these are 3 patterns of eliminating a null pointer error warning. So now we can apply those in this code snippet. So there is only one way of applying P1, there is only one way of applying P2, but there are 3 ways of applying P3. Now, if you are an IDE person or a compiler person, you can see that many of them can be ruled out obviously. There are obvious, this in the last one in P3, after return, the control doesn't reach after return. And in the first one, the variable v is not even defined yet. In P2, there is an alternative path where no return has been specified, and so on and so forth. So you could have taken care of eliminating some of these just by static analysis, but getafix is purely syntactic. So let's say we have just this purely syntactic way of predicting patterns, and now we need to figure out what do we do with these. So obviously not all of them are correct. So we want to apply patterns to a new bug to get candidate fixes. So here is our pattern P, which says H0 goes to if X not equal to null H0. Okay, so well, one thing you could do is that you could certainly apply at each of these statements, or almost each of these statements. You can obviously apply it at the statement where the comment says B is equal to null pointer error here. So we are just matching where this pattern can be applied. So it matches here. It can be applied to the next statement as well. Maybe you don't want to, but it can be applied. Or you could in fact wrap the entire while loop into a null check, and syntactically that is allowed as well. You probably don't want to wrap only the last line of the closing bracket there. Now, some of these actually will fix the warning. Maybe it's not the right way of fixing it, but here by fix, you could imagine that the tool runs again. So infer would run again and tell you that these code changes actually led to correctly, or maybe not human correctly, but still from a tool point of view, fix the issue. So the one that shows against x.f, that clearly is the right place to fix, and that works fine. If it turns out that if you encapsulate the entire while loop in a null check, that will also fix the issue because of how many static analyzers work. Maybe that's not what you want to do. And then wrapping the important side effect call is not going to fix the issue. And here by H fix, we mean what the human would, how the human would fix things here. Well, the human would obviously be adding a null check exactly at the line x dot f and not at other places. Okay, so those are our choices. So let's formalize this a little bit. We asked the question that, a fixed candidate is you apply pattern P, Z lines from bug B, and Z is kind of an offset from the line from where bug B is reported. The match part is just simply enumerating all the places where you can apply this bug, and you can see that quite easily. The validate part is that you can now rerun infer or your static analyzer and find out where all the tool fixes or which of the applications actually quiet down that particular warning. And then finally you can show the human, and the human will say, yeah, this application of the fix is right, and this application, this other application, or these other applications are not right. Now we want to be sparing in asking the human, because human attention is one of the most precious commodities there is. So we don't want to resort to hfix if we can avoid it. And it also turns out that in fact rerunning the static analyzer on a large code base can be expensive, in computationally expensive. So you want to do that sparingly as well. So what that leaves us with is that you want to just try to rank all the places where a syntactic match in terms of application of pattern P can be done. Now, I would like to stop here for just a second and contrast it with lot of existing literature in program repair, where the idea of generate a candidate fix and check, and that can happen in a loop, and that works in many cases. People have published very nice ideas in that context. But for us, one of the issues there is that we cannot even validate too many variations without an exorbitant computational cost. So we resort to just ranking, and we validate our highest ranked fixed proposal just one time, and that's it. So let me then quickly tell you about how this ranking happens. In terms of a model, you could imagine that you want to you can compute this probability of a certain syntactic match being the human fix. And if you have lots of training data, you can at a new occurrence tabulate this and figure it out, but that also will take a long time to compute because you have to figure out all the matches. So we approximate it essentially by a product of three ratios: prevalent, or rather scores: prevalence, location, and specialization. What prevalence says is what is the relative frequency of a bug fixing pattern in training data. Higher prevalence is more likely to be right. What fraction of the fixes were Z lines away from the point of the bug report? And here you can see in the lower right corner, in the existing training data, there were no occurrences where the fix was after the blame point. So it got the score of 0, but other places did not get score of 0. And then finally, there is a notion of sort of a specialized fit, which is the reverse of average AST nodes matched by a pattern P. So the more specifically a pattern P matches somewhere, the more likely it is to be the correct one. So once you take all these scores into account, here fortunately the math works out fine, and you choose P1 as the correct fix. So that is how GetAFix proposes fix. I would like to leave with some thoughts here, saying that fixing of small bugs is not the only thing GetAFix is designed for. There are other routine things that we can do. So some of them are listed here. Developers have to fix bugs, but they have also to review code and refactor code. And then at least we believe that many developers would prefer to spend time not on routine activities, but rather on what they think is more exciting work. The definition of more exciting, of course, differs from person to person. But let's say that there are a set of more exciting things that they would rather do than do routine work. So we talked about fixing these simple static analysis kind of bugs as one thing that can be automated based on historical training data. Another thing you could, and we kind of showed the goodness of it in our situation. Another thing you can do is automatically try to review code, because you can see from historical data which code changes were triggered by a code review. So another engineer put in a review comment, and then the engineer who wrote the code commit has to go ahead and make that change in order to make sure that all the code review comments are handled. Now, it turns out that some of these code review comment themselves could be predictable. And furthermore, the way to remedy those code review comments could be predictable as well. So you could try to do both of those things based on your training data. And then finally, you can also identify opportunities for refactoring by looking at just how other code has been refactored. So on this slide, I have shown 3 cases where maybe all of these are sort of better Java usages compared to what was written before. And I think what we did here was we looked at lots and lots of code revisions from open source code repositories. And we said, okay, let's find repetitive refactoring like changes. And these and many others popped out. And now you have kind of a good way of trying to recommend refactoring changes for your own repositories. So GetAFix can actually get at all of these use cases as well. Let me then flash this slide that I have shown a couple of times before, that scale truly presents an opportunities. You have lots of different kinds of artifacts that are produced in the course of software engineering. And we talked about 2 specific examples of how you can leverage this data along with machine learning to build interesting models. But these are not the only problems that can be addressed. There are many, many such problems. So there are opportunities in all phases of software lifecycle. In an individual developer workflow, for example, people want to know, how do I do this? That's searching for related code. Or everyone expects a very good autocomplete, or they want simple bugs to be fixed automatically, which is program repair. Or you can look at the workflow that is about integration and release, which is peer code review, test selection, release readiness prediction, and things of that nature. And then likewise, you could also use these ideas in post-release workflows. For example, we got all these bugs from the field. What do we do with them? Who should fix them? And so on and so forth. I noticed that MSR community has been particularly active in this third pillar here. So I'll not say much more about this, but we do expect to continue to use many of these ideas, lightweight machine learning, in our own practices. I'm done. I'll leave you with this last slide. There are some references to work that has been done from our team. More work is in progress. Let me stop here and take questions. Thank you very much.
Thank you very much. So we do have a lot of questions.
Okay.
Yeah.
Should I stop screen sharing and go to Slack, or are you going to just read them out to
we
me?
We can read them out for you, I guess.
Okay, and I can offline maybe respond to some as well if we don't get to all of them.
Sure. So
I'll go by the highest rated ones, highest voted ones, I guess. So the first question is from Diomedes Benelis from University of Athens, and it's, have you studied the human aspect of corrective suggestions? So how likely is it that developers will blindly accept a wrong fix because it's suggested by the computer, and how likely that the fixed suggestions only plaster over the problem, really then solve the underlying cause?
Yeah, so excellent questions. For the first one, we believe that people definitely are looking at the computer-generated fixed suggestions, because notice that at the time we did this measurement, only 40% were being accepted, and people would sometimes write semantically equivalent fix and sometimes a completely different fix, and so on and so forth. So I think people are being careful in terms of not just blindly pressing accept and move on. So that's the answer to the first question. The second one is very interesting, whether these are actual fixes or we are just plastering over the issues. And in these examples that I showed, it could appear that way. So one thing to note is that these are in fact the kinds of fixed patterns that exist in the repository. And so the premise here is that the human was going to do the same thing again given that particular warning anyway. So we are essentially just trying to save the human the effort of making this change, predicting that they would have made a similar change anyway. Now, is that a real fix or not quite? This question comes up a lot. It turns out that many times it is in fact better to, on the one hand, you have a guaranteed null pointer exception that you might then have to sort of either you result in a crash or you have to catch it elsewhere, or you kind of bypass that. Now, is bypass always correct? No. But in Android, it turns out that there are many of these entities such as listeners and so forth that you can, if they are not null, then you need to do something, otherwise you do nothing. So we believe that a lot of these cases are not that people are just being lazy and patching over a problem right for this moment. Many times this in fact is quite okay. But having said that, it's definitely not a guaranteed logically correct fix in every single time. Yes, so that's kind of a longish answer to that question, but it's a great question.
Right. So the next question is actually a question by me. So many of the ideas you presented here are actually based on existing research that some of it has been around for a while, right? So what challenges did you face kind of applying this research at scale at Facebook, and kind of what is the tech transfer story behind this?
Yes, again, a great question. For the GetAfix one, one of the constraints that we worked with was that we cannot really run the validator over and over again. So we propose a fix and we resort entirely to ranking, and then we validate only the top ranked fix and we show it to the human. This, I think, differs from most of the work that I have been aware of in the space of program repair, where it has been in those settings easier to take, let's say, a test suite, and you rerun the test suite after proposing a fix, and if it fixed that test, you kind of gave a positive score to that proposed fix, and so forth. So this issue of running a validator, whether it's a static analysis or a test suite, in our constraints, we couldn't really do literally that. That was kind of not a possibility. So that's why we had to work on ranking quite a bit. I could say similar things about the first part of the talk that was about test selection, but in terms of question diversity, maybe we want to move on and look at other questions.
So actually the next question is about test diversity, so maybe that can play as well. So this is by Tim Menzies from North Carolina State University. So his question is, you don't test everything, which is understandable given the size of your systems, but did you look at the impact of the things not tested? So basically, what do you lose by not testing everything?
Yeah. Okay, so one thing so first of all, hi Tim. Then one thing I did not call out, but I should have called out, is that it is not that we don't test things. If you remember in a slide long ago, there was this third row of red boxes at the bottom. Let me quickly see if I can make it go there. And it's an excellent observation. So the short answer is that no, we do actually in the end do test everything. So when things are about to join here in the red release readiness, so every few hours, in fact, every single test is in fact run. What we are economizing here is primarily not having to rerun tests over and over again in the evolving master branch. But every so often we do test everything. So no test is kind of truly dropped before release. So that's the answer to that.
Okay, I think we have time for one or two more questions. So
okay, so we'll go quickly here. So the next question is by Georges, actually, and so the question is, many of the issues that the predictive test selection work try to fix are due to the fact that the dependencies are at the directory level. Would it make sense to make the dependencies more fine-grained, and how would you go about doing that? I guess Georges is here.
The answer to the first question, I think, is yes. The first part, that yes, it would be great to be able to capture dependencies at a fine grain level. How we would do it in our context, I don't know. We haven't really thought that carefully about that, but it is a promising direction how we can capture these in a more fine grained basis.
I'll take the last question and then we wrap up. So that question is from Ayushi Rastogi. And her question is, if code reviews are predictable, at least to some extent, when are these suggestions given to developers? During development or during code review time? I'm guessing probably the fixes and things that you want to change in your code.
Yeah, so it is. It can be done at many levels. When the code is first of all, I should say that human code review serves many purposes, and the goal of GetAfix is not to automate it completely. We are only trying to automate which things that look like entirely predictable kind of code review comments, because human reviewers shouldn't be spending time doing that. So that's one thing. Now, you could imagine doing this at many places. You could, in fact, many of these ideas could be done at the IDE level itself, that when a human shows intention of submitting the code for review, before that, you can imagine an automated code review phase already shows some of these code review comments, and the user gets to the developer gets to address them right there. Other thing that could happen is that as soon as some code enters this repository management and code review system, first these automated things are pre-populated, so the human reviewer, when they come along, they see, yeah, these things already are generated by some tool. I don't have to spend my time doing this kind of nitpicky routine comments, and they can save their time at that point. And likewise, when the human comes back to see how his code was commented on, they might be able to also see proposed fixes, which is kind of where we show proposed fixes in the code review system anyways. So there are multiple places where these kinds of things can sit in the workflow, IDEs or in a code review portal or what have you.
Okay, thanks a lot. So if you have more questions, actually definitely you can leave in the Slack channel, and then our speaker will, or other people can discuss further about this topic. It's very interesting. Once again, thanks a lot for the great talk, and then it's just amazing. Let's thank him one more time. And thank you very much.
Thank you.
This will conclude this session.
Thank you, Satish.
Thank you.